Ever wondered what it takes to make the perfect potato chip? It's far more than just a simple recipe. It's a 15-year biological journey from the soil to your snack bag. Most of us see potatoes as static commodities, but the truth is, they're alive, they're respiring and breathing. And right now, researchers are battling a hidden biological wall in cold storage that can ruin an entire crop's quality in just days. Today, we're uncovering a major bioengineered breakthrough from Michigan State University that is rewriting the rules of the supply chain. Let's dive in.
Okay, let's dive right into this. Just take a second to read that quote on the screen. I mean, most of us look at a potato sitting on a grocery store shelf, and honestly, we just think of it as a rock, right? Just a completely static, dead, inanimate object waiting to be eaten. But David Doches, he's a leading researcher at Michigan State University. He completely shatters that misconception. Potatoes are actually respiring, breathing entities. They are alive, and the second you pull them out of the ground, that clock starts ticking immediately.
So those freshly dug potatoes resting in the dirt? They aren't just these simple, earthy commodities. They're actually highly dynamic biological systems. Because they're living organisms, they actively react to their environment, especially when it comes to changes in temperature. And as we're going to see today, understanding and actually engineering this living, breathing response, well, it's literally the difference between a multi-million-dollar agricultural success and a complete supply chain disaster.
Welcome to this explainer. I am absolutely thrilled to guide you through this fascinating, really high-stakes story of potato breeding, logistics, and bioengineering. We're looking at a 15-year biological journey, taking us all the way from the soil to the absolute perfect potato chip. It's this incredible story that perfectly bridges raw agriculture, cutting-edge genetics, and massive industrial supply chains.
So, here's our map for today. First, the Respiration Paradox. Then, the 15-year genetic funnel. Third, the cold storage dilemma. Fourth, the bioengineered breakthrough. And finally, rewriting the supply chain.
All right, let's jump straight into Section 1, the Respiration Paradox. Potatoes breathe. It's time for a bit of an agricultural reality check. You know, we aren't just talking about a simple side dish at dinner here. When you look at massive potato processing facilities, we are talking about a colossal economic engine. Just to put it into perspective, in places like Michigan, which actually leads the nation in chip potato production, a staggering 70% of the entire state's potato crop goes strictly to chip processing. 70%. So optimizing these specific chipping varieties isn't just some fun little science experiment. It's an absolutely urgent, massive operational priority for growers and processors. If the potatoes don't behave exactly as needed, well, the whole system just grinds to a halt.
Moving on to Section 2, the 15-year genetic funnel, breeding perfect chips.
Here's the thing. You can't just slice up any old potato and expect to get a commercial-grade chip. It doesn't work that way. The raw potato has to fit exact commercial bag dimensions seamlessly, and even more importantly, it absolutely must withstand high heat frying without breaking down. Now, it takes 15 long years to breed a new variety. Why? Because researchers aren't just looking for perfect processing quality. They're simultaneously trying to lock in vital traits like climate adaptation and resistance to diseases and pests. It's like a giant puzzle. Trying to fix one desired trait without accidentally losing another is incredibly difficult.
And this really illustrates just how punishing that genetic funnel actually is. Every single year, over 225 new varieties are evaluated by the National Chip Program. Out of all those, maybe 100 advance for further trials out in the dirt. Fast forward to today, and there are only about 50 elite varieties actively used for all U.S. chip production. To show you how rare commercial success truly is, over the last 15 years of dedicated research, Michigan State University's David Doches has successfully developed just 5 commercial chip varieties. 5. Out of thousands of attempts over 15 years. It is an incredibly steep climb. That brings us to Section 3, the cold storage dilemma, hitting the biological wall.
So the primary supply chain conflict in the snack industry is basically this. How do you keep a living commodity fresh all year round? Biology is directly fighting against industry here. Look at the numbers. If you store your potatoes at a traditional 50 degrees Fahrenheit, you get good processing quality. But because the potato is respiring relatively quickly, your shelf life is severely limited. They spoil fast. Now, if you drop the temp to 45 degrees, using newer varieties like the Manistee, you can safely extend that storage window all the way through July. But the absolute holy grail for logistics, that's deep cold storage at 40 degrees Fahrenheit. That gives you maximum shelf life. But historically, hitting 40 degrees triggers this massive biological wall. The potato literally reacts defensively to the deep cold by aggressively spiking its internal sugar levels.
And here's what that biological wall actually looks like in practice. It's a process called cold-induced sweetening. On the left, at day 0, you've got a freshly harvested potato. The starches are completely intact, and it yields a perfect, translucent, golden chip. But as your eyes move to the right, toward day 120 in cold storage, you see this dramatic change. Prolonged cold causes that respiring potato to defensively convert its starches into sugars. So by day 120, it is just packed with excess sugars.
Now, why exactly is that a problem? Well, when those freshly sliced potatoes hit the vats of boiling oil, all those excess sugars from the cold storage rapidly caramelize and burn. They don't turn golden. They turn dark, brown, and intensely bitter. The result is a chip that snack manufacturers are absolutely forced to reject. You lose the entire crop, and you lose millions of dollars. No way around it.
Which leads us to Section 4, the Bioengineered Breakthrough, overriding the wall. This is where the narrative really shifts to a paradigm-shifting solution. Out there right now, massive tractors are harvesting the absolute cutting edge of agricultural research. Michigan State University has actually developed a newly bioengineered potato that's currently in seed production for commercial testing.
So what exactly does this breakthrough do? Well, this bioengineered variety is specifically designed to maintain its sugar balance even when it's plunged into that 40-degree deep cold storage. It entirely overrides that biological wall of cold-induced sweetening we talked about earlier. By safely holding at 40 degrees without converting starch to sugar, it drastically reduces spoilage rates, completely prevents that dark, bitter frying, and vastly extends the viable processing window. It's a true game changer. This is what happens when you have a perfect dynamic collaboration between agricultural researchers listening to the exact needs of end processors and local growers.
Finally, Section 5, rewriting the supply chain. Local, year-round sourcing.
When we zoom out, we can see the massive logistical impact this single biological tweak has on the real world. The old way? It was defined by national vulnerability. Because local potatoes just couldn't be stored long-term without burning in the fryer, processors had to rely on constantly shipping fresh potatoes from all across the country as the seasons changed. I'm talking huge logistics costs, massive carbon emissions, and constant supply chain delays. But the bioengineered future? That creates year-round local sourcing. Because we can now use enhanced cold storage at 40 degrees without ruining the potato, processors can actually source their raw materials locally all year round.
To put that into perspective and prove just how impactful this really is, listen to Phil Guzmano from Better Made Snack Foods. He says, "We're not shipping potatoes from all over the country. Instead, they're being shipped from an hour and a half away all year long." Just think about that for a second. By bioengineering a potato to simply not produce sugar at 40 degrees, you completely eliminate thousands of miles of diesel trucking from your entire supply chain. You slash transit times, you boost operational efficiency, and you dramatically lower your carbon footprint.
And here is the deeply satisfying conclusion to our 15-year biological and logistical journey. Perfectly golden potato chips, tumbling cleanly off the commercial processing line. This isn't just a static snack. It's the final output of a dynamically engineered, perfectly balanced biological system. Every single chip in that frame represents over a decade of genetic trials, overcoming complex plant respiration, and literally rewriting global supply chain logistics.
So I'm going to leave you with a final, provocative question to think about. As agricultural bioengineering continues to build a more resilient, efficient, and locally sustainable food supply chain right under our noses, what other everyday commodities sitting in your pantry right now are just waiting for their own 15-year breakthrough? The science of our food is never static. It's always breathing. Thank you so much for joining me on this explainer. Keep learning, keep questioning, and I'll catch you next time.
Welcome to the debate. You walk down a grocery aisle, you grab a bag of potato chips, and you probably assume the raw material was just like a static rock pulled from the dirt.
Right, which isn't quite true.
No, not at all. They are living, actively respiring biological systems. So today, we're unpacking the 15-year biological journey of U.S. potato breeding for chip production. We're asking, does bioengineering these cold storage potatoes represent a vital economic evolution to save local supply chains?
Or is it just an over-engineered agronomic solution to satisfy the rigid demands of industrial fryers?
Exactly. I'll be arguing that this genetic leap is, frankly, an absolute logistical necessity.
And as an agronomy engineer, I'm taking the perspective that we are unnecessarily warping biology just to meet the aesthetic constraints of industrial processing.
Let's look at why this bottleneck even exists in the first place. In places like Michigan, which leads the nation in chip production, something like 70% of the entire crop
goes straight to chip processing.
Which is a massive volume.
It's huge, but because these potatoes are actively breathing organisms, storing them at the traditional 50 degrees Fahrenheit, it severely limits their shelf life. You get maybe a 2 or 3 day window before rapid respiration and spoilage just completely set in.
Yeah, they go bad fast.
Right. So breeding a potato that can survive at 40 degrees deep cold storage is a total economic triumph. It safely pushes those biological limits down and secures a processor's local supply chain.
Okay, but are we actually preventing waste here, or are we just, shifting the burden? Because when you drop that temperature down to 40 degrees, you trigger what we call cold-induced sweetening. And it's really crucial to understand exactly how that works biologically.
Right, the sugar conversion.
Yes, the potato isn't failing at that temperature. It's protecting itself. It rapidly breaks down its starches into sugars because those sugars act like a cellular antifreeze. They prevent ice crystals from forming and rupturing the potato's cell walls. It's a brilliant biological defense mechanism.
A defense mechanism that unfortunately completely ruins the chip.
Exactly. But the only reason this is framed as a quote-unquote dilemma is because industrial processors demand uncompromising aesthetic perfection. When those high-sugar potatoes hit the high-heat fryers, the sugars caramelize, right? They burn.
You get those dark, bitter chips.
Right, which processors immediately reject. Throw in the demand for raw potatoes that perfectly fit commercial bag dimensions. And you see my point. We are fundamentally forcing biology to conform to industrial machinery.
I get the hesitation, I do. But it goes far beyond just getting a perfect golden fry. This is about basic supply chain survival. Without these cold storage varieties, local supply chains essentially collapse every single winter.
But they wouldn't collapse if we just...
Well, think of bioengineering this trait like installing a thermodynamic thermostat inside the potato cells. We are basically reprogramming the exact temperature at which the plant decides to deploy that sugar antifreeze. Under the old system, when local Michigan supplies spoiled by January, processors had to ship potatoes all the way from the other side of the country.
Which is expensive, sure.
Drastically increased logistics costs, massive emissions, much higher risks. Now, facilities can process potatoes shipped from just an hour and a half away, year-round. Plus, this kind of advanced global potato breeding tackles critical issues like disease resistance in places like Rwanda and Bangladesh.
I don't deny the logistical benefits. I really don't. But you have to look at the sheer scale and inefficiency of the genetic funnel required to get there. It is highly disproportionate. The National Chip Program evaluates, over 225 new varieties annually?
Something like that, yeah.
Yet researchers have successfully developed just 5 commercial chip varieties in 15 years.
Which speaks to how rigorous the supply chain standards are.
No, it speaks to how biologically stubborn the plant is. Breeding potatoes isn't like breeding other crops, because potatoes are tetraploid.
Meaning they have 4 copies of every chromosome instead of the usual 2.
Right, so trying to pass down that specific cold storage trait without bringing along undesirable traits like poor yield or, disease susceptibility is like trying to roll a pair of dice and land the exact same number on 4 distinct dice at the exact same time. It's an agronomic nightmare.
It's difficult, sure.
We are spending decades of elite genetics entirely overriding a plant's biological wall. Why not just adjust the processing parameters, tweak the fryers to handle a slightly higher sugar balance, rather than bending agronomy over backward to serve the machines?
Because tweaking the fryers doesn't solve the fact that a respiring commodity will literally rot before it reaches the plant. Ultimately, bioengineering these potatoes completely rewrites the supply chain map. It turns a massive national vulnerability into a resilient, efficient system of year-round local sourcing that benefits the grower, the processor, and the environment.
And while the science behind manipulating that cellular thermostat is undeniably impressive, it really highlights the extreme lengths we go to. We are dedicating decades of complex tetraploid genetic research to serve static industrial parameters rather than adapting our machinery to biological realities.
Well, optimizing a living commodity clearly requires a delicate balance between those agricultural limits and processor specifications. We'll leave it to you, the listener, to consider what truly drives the food on your shelves. So next time you hold a potato chip, Remember, it isn't just a sliced rock from the dirt. It's the final output of a dynamically engineered, perfectly balanced biological system.